Welcome to my dissertation presentation on GPU-driven rendering performance analysis. I'm demonstrating a DirectX 11 rendering engine that I built to compare traditional CPU-driven approaches with modern GPU-driven techniques using compute shaders. Traditional CPU-driven rendering follows a sequential pattern. For each object, the CPU performs frustum culling, generates world matrices. Rendering 5,000 models individually results in 5,000 separate draw calls, sequential processing, and significant CPU overhead, with an efficiency of just one object per draw call. Is there a better way? Enter GPU-driven rendering. My GPU-driven solution uses a 4-stage compute shader pipeline: world matrix generation, frustum culling, stream compaction, and draw argument updates, all happening in parallel on the GPU. The revolutionary result: 1500 times draw call efficiency improvement, from 1500 individual calls to one indirect draw call. That's 149,900% better efficiency. While the FPS gain from 70 to 90 frames per second at 1500 objects might seem modest at first, the real story is in the efficiency. 1500 times better draw call handling, scalable and a future-proof architecture, better hardware utilization, and a 35% boost in memory throughput. Now let's see this in action. Here's my DirectX 11 rendering engine, initialized with 5,000 spaceship instances. You can see the full list on the side. I can toggle between CPU-driven and GPU-driven rendering in real time using F12. Visually, things may look a bit similar, but under the hood, it's a completely different story. With around 1500 spaceship instances in view, GPU-driven rendering gives about 20 more frames per second. Let me show you the performance metrics. This performance monitoring system tracks 26 real-time metrics. Let me highlight the key efficiency improvements. Model rendering efficiency. CPU requires one individual draw call for one visible object, while GPU uses one indirect call for all the visible objects. That's a lot better efficiency. Frustum culling. CPU takes 5,000 microseconds while GPU takes 10 microseconds. GPU utilization. CPU-driven only achieves 65%, while GPU-driven achieves 85%. These metrics update every second, showing the real-time impact of our architectural changes. The benchmarking system provides controlled performance analysis. Let me configure a benchmark. I can select rendering mode, object count, and benchmark duration. Let's run a 60-frame benchmark comparing both approaches. Watch the progress bar and status updates. The system is simulating rendering frames, collecting performance data for each approach. Here are the results. The GPU-driven approach shows our performance gains. I can export these results into a CSV file. This research demonstrates that improving efficiency can be more impactful than simply increasing raw performance. The efficiency improvements lays the groundwork for advanced techniques such as GPU-driven level of detail selection and hierarchical occlusion culling. Furthermore, by leveraging a compute shader-based GPU-driven rendering pipeline, the CPU is free to focus on other critical tasks, including game logic, AI, and physics simulations. Thank you for watching this demonstration of GPU-driven rendering performance analysis.